empezó un nuevo curso de la escuela, la profesora Carmen Nuñez, de la Universidad de Buenos Aires, y va a hablar sobre Introduction to String Theory. Y queremos preguntarles si quieren el curso en castellano o en inglés.
Castellano.
Algunas levantadas de manos.
Levantada, sí, levanten la mano.
¿Cuál es?
Español. Español.
No, pero hay varios que no.
Inglés.
Y los de probablemente.
Okay, so I think I'll do it in English. So sorry for the Spanish. I'm slower in English, so okay, so I want first to thank the organizers, especially Hugo, and to congratulate them for very good organization. And okay, so I'm going to talk about the superstring, introduction to superstring. And the plan of my talk is today I will try to do the classical fermionic string. Tomorrow I will try to do the quantization and obtain the spectrum of the superstring. Then, depending on how the time goes, I'll do the partition function and finally interactions with the scatter. Okay, so today I will first discuss the action of the superstring and its symmetry. I understand Nathan did some of it. Repeat. Then I will do the gauge fixing and constraints, equations of motion and boundary conditions, and finally the oscillator expressions. Okay, so why do we want to do superstrings? You have been learning from Professor Silva a very nice theory, which is the bosonic string. It has many nice properties. For instance, the theory has no free dimensionless parameters. This is something very interesting in a theory. You know, from the standard model, there are many free dimensionless constants. And by taking different values for these parameters, you get different theories. Here, this bosonic string theory has no free parameters, dimensionless free parameters. So this is a nice property. The theory, the consistency conditions of the theory determine the critical dimension. This is also something very interesting because in field theory, one is used to putting the dimension from the outside. One formulates a theory in 4 dimensions, but one can formulate it in any dimension. String theory, consistency, mathematical consistency of the theory determines critical dimension. The theory contains a massless spin 2 field. We've seen today the spectrum of the closed bosonic string, and this you have not seen yet, but we'll see that interactions of this field reduce at low energies to general relativity. The theory has no ultraviolet divergences, so this gives a consistent theory of quantum gravity. The theory of the open string contains a massless spin 1 field, whose interactions reduce to the Yang-Mills theory at low energies. And consistency of the theory requires large gauge groups, which is interesting because these large gauge groups allow to incorporate the groups of the standard model, so one can do phenomenology in some sense. But despite all these nice features, the bosonic string contains a tachyon, and the tachyon indicates some instability of the vacuum. It indicates that the vacuum has not been correctly identified. For instance, if you look at the mass of a particle, in the action is the quadratic term, the second derivative of the potential gives the mass square of the particle in the action. So if it is negative, it means we are expanding around a maximum of the potential. And the question is if there is some stable minimum. And so, I mean, expanding around a maximum is not a real inconsistency, but the question is if there is a real minimum. So this question is difficult, actually. It's a complicated question, and I think we don't have an answer. So if we expand the potential, the term TQ gives a minimum, but T4 destabilizes it again. So we don't really know if there is a stable minimum in the theory. Moreover, the tachyon gives infrared divergences in loop diagrams, so it is not a nice feature for now. The critical dimension, so as I said, it is nice that the theory determines the dimension, but the critical dimension is 26, which is a bit too high. And moreover, the theory has no fermions. All degrees of freedom are bosons, so we would like to describe nature, and we need fermions. So we will see that all these shortcomings can be overcome if we construct a theory with worldsheet supersymmetry. So we will associate to each bosonic degree of freedom. So in the bosonic string, we have the bosonic fields x mu of sigma and tau on the worldsheet. These are bosonic degrees of freedom. So we will introduce some fermionic partners, psi mu. This will be Majorana fermions, and this will be partners of the x mu for a worldsheet n equals 1 supersymmetry. So we will construct a theory with n equals 1 supersymmetry on the worldsheet. So we will see in this theory, Gliozzi, Sherk, and Olive showed in '77 that it is possible in this formulation to get a theory with no tachyons and with equal masses and multiplicities for bosons and fermions. And Green and Schwartz showed in 1980 that this model has space-time supersymmetry. So we will construct a theory which has n equals 1 worldsheet supersymmetry. But we will see that this will allow us to obtain a theory with space-time supersymmetry. So in this theory, in this superstring theory, the one-loop diagrams are finite, they're completely finite, and free of ultraviolet divergences. But in the same way as in the bosonic string, we would like to avoid the negative norm states. And so if we couple this, so if you remember today, Barton introduced the Polyakov action, which couples, the Polyakov action couples these fields, x mu, to a two-dimensional metric on the worldsheet. And the ghosts in the theory are removed by imposing the constraints, which are actually the vanishing of the energy momentum tensor. So the way to obtain a ghost-free theory in the bosonic case is to impose these constraints, the vanishing of the energy momentum tensor, which is basically the equation of motion for the two-dimensional metric. And so the absence of negative norm states depends crucially on reparametrization invariance. So we want to construct a two-dimensional supersymmetric theory with reparametrization invariance. And so we will see that the way to generalize this, so the Polyakov action couples the bosonic field x mu to a two-dimensional metric. So now we would like to couple the supersymmetric matter, let's say x mu and psi mu, to a two-dimensional supergravity. So we would like to add to this theory two-dimensional supergravity, which would be the generalization of the Polyakov bosonic string. Okay, so we will see that. This action, in this action, and imposing the equivalent constraints to the vanishing of the energy momentum tensor, all the negative norm states will decouple from the theory, and we'll see that consistency will require 10 space-time dimensions instead of 26 that you obtained in the bosonic case. Okay, so as I said, although this construction has n equals 1 supersymmetry on the worldsheet, it does not have supersymmetry in space-time. So to get a supersymmetric spectrum, we will have to do what is called a GSO projection on the states of the theory. We will have to eliminate some of the states of the theory, and this will give us a 10-dimensional space-time supersymmetric theory without tachyons. So this construction that I will be discussing is called the Neveu-Schwarz-Ramond superstring. And as I said, it has a worldsheet supersymmetry, but space-time supersymmetry is not manifest. We will have to impose a projection to get a supersymmetric space-time theory. There is also another formulation of the theory which is called Green-Schwarz formalism, in which space-time supersymmetry is manifest, but worldsheet supersymmetry is not. But in this theory, it is difficult to compute interactions, so I will not discuss this theory. And moreover, there is also a covariant extension of the Green-Schwarz formalism, which is called the pure spinor formulation. And Nathan here is who constructed this formulation. I will not discuss this because I don't know how maybe he should do it. So one could wonder if there are other possibilities. So I said we take n equals 1 supersymmetry on the worldsheet. What about taking extended supersymmetry? For instance, why don't we take n equals 2 supersymmetry or n equals 4? It turns out that for an n equals 2 supersymmetric worldsheet theory, the critical dimension turns out to be 2, so it is a bit low. And if we try to formulate a theory with 4 supersymmetries on the worldsheet, the critical dimension is negative. So we will strict to n equals 1 supersymmetry. And there is also another construction, which I will not have time to discuss, but probably Narayan will discuss it next week, which is the heterotic string. Similarly, as in the bosonic string, we will see in the superstring that left movers and right movers are independent. So one can take a mixture, one can take, say, a bosonic theory for the left movers and a supersymmetric theory for the right movers. And this gives rise to what is called the heterotic string. So this gives rise, the heterotic string gives rise to an n equals 1 theory in 10 space-time dimensions. I won't have time to discuss this. Okay, so let us try to construct the action of the superstring. So we want to supersymmetrize the Polyakov action. So let me recall the Polyakov action. It was written this morning. So it is basically the coupling of two-dimensional metric. So it is the coupling of a two-dimensional metric. So I will use these coordinates alpha, beta, will denote actually sigma and tau. So this will take values 0 and 1, referring to tau and sigma coordinates on the worldsheet. So H alpha beta is basically, well, is a metric in 2 dimensions. And eta mu nu is the space-time metric. I'm taking a Minkowski metric for the space-time. So as I said, the supersymmetric extension of this theory would be to couple supersymmetric matter to 2-dimensional supergravity. So these x mu fields are scalars on the worldsheet. So this mu index is a vector index in space-time, but these fields are scalars on the worldsheet. So we will add to this theory fermions, Majorana fermions. This psi mu will be Majorana spinors. So, okay, so we will try to couple this theory. And so we can consider this action. So let me, well, it's written there. So this psi mu, as I said, is a Majorana spinor. Psi bar is the conjugate spinor, which is obtained just in this way. Psi bar is the adjoint times rho 0. Here rho alpha are the Dirac matrices in 2 dimensions. For instance, okay, a convenient parametrization is in terms of Pauli matrices. For instance, I can take this parametrization. These are Dirac matrices in 2 dimensions. So I will take this real representation. And so these Dirac matrices satisfy the 2-dimensional Clifford algebra. Of course, these are not constant. One can construct the constant matrices acting with the Filbine, and we'll not discuss this, but I mean, one can convert curved indices into flat indices using the Filbine, and then these are the constant matrices which satisfy the Clifford algebra with the Minkowski metric on the dimensions. Okay, so we can also define the analog of gamma 5 in 4 dimensions, which in 2 dimensions would be the product of rho 0 and rho 1, which has this. So, questions here?
There's one question. The second term in the action looks somewhat like a Dirac operator, but then why there is no spin connection?
Good question. That was my next comment. Why there is no, I will explain that. So first of all, let me say that I have not written spinor indices here. So I will not write this, but then if I write the spinor indices, they are raised and lowered with the charge conjugation matrix, which in this case is rho 0. So okay, so these 2-dimensional spinors, I will take components plus and minus. These are spinor indices. And so to raise and lower, so psi plus with an upper sign will be minus, psi minus with a lower sign, and psi minus equals psi plus in this way. So these are some of the exercises you are supposed to do. And to understand why there is no spin connection here, one has to use these properties which hold for Majorana spinors. For instance, this spin flip property. So the spin flip property says that the conjugate spinor, say 1, times a product of row matrices, row alpha 1, row alpha n, times another spinor equals -1 to the n. So the conjugate of the second spinor times the product of row matrices in the opposite order, alpha n, alpha 1, lambda 1. So you see that if you use this property, which holds for Majorana spinors, then here, since we have lambda 1 and lambda 2 are the same, they're psi mu. So if I write this, so with only one matrix, then I will get a minus sign here, and the spin connection I mean, has no indices, so that term vanishes in 2 dimensions. So I could write covariant derivative, but the spin connection term will not contribute. Okay, so this is an important property, the spin flip property for Majorana spinors, which we will be using it many times. Another interesting property is the fierce identity. I won't write it because I will use it only one time, and so I will recall it later. But another important property for these Dirac matrices is this one here, the product rho alpha, rho beta, rho alpha equals 0. So these are 2 very important properties that we will be using over and over again. And this product of gamma matrices, this follows just from the Clifford algebra. Rho alpha, rho beta is the 2-dimensional metric plus the equivalent of the gamma phi. Yes?
¿Por qué, además de usar spinores Majorana, por qué no podríamos usar spinores de Weil?
Okay. Shall I answer?
Sí, okay.
Porque en realidad, o sea, vamos a ver que son los spinores de Majorana los que dan una construcción interesante. O sea, para supersimetría generalmente se usan spinores de Majorana, porque el número, uno quiere que si tiene una teoría supersimétrica, la cantidad de grados de libertad bosónicos y fermiónicos coincidan, y la manera más económica de hacerlo es con los spinores de Majorana. Entonces, generalmente en teoría supersimétrica uno trabaja con
Sorry, no question. Why do we want a theory without tachyons?
As I explained in the first transparency, the tachyons indicate an instability of the vacuum. I mean, it means that we are expanding. If we have a tachyon, it means we are expanding the theory around a maximum of the potential, and that is unstable. So, so that is actually not a real problem if there is a real stable minimum. So it just means that we picked the wrong vacuum to expand around. But we don't know in this theory if there is a real stable minimum. So, I mean, so it is not a real inconsistency, but we don't understand very well the tachyon. Okay, so let us work out the balance between bosonic and fermionic degrees of freedom. So the x mu provide d bosonic degrees of freedom. This is d bosonic degrees of freedom, and the Majorana fermion provide 2d because so I haven't written it here, but Majorana fermions, they have 2 components, psi plus and psi minus. So this provide 2d fermionic degrees of freedom. Okay, so we need to add some an auxiliary field, which is usually called mu. which provides other d bosonic degrees of freedom if we want to have the same number of bosonic and fermionic degrees of freedom. So this is what we just said. So together, these fields x mu, psi mu, and f mu form an off-shell multiplet of two-dimensional n equals 1 supersymmetry. But we can, on shell, these the equations of motion for the f mu field put it to 0, so we can basically eliminate it, and these 2 degrees of freedom on shell, they suffice to obtain an n equals 1 supersymmetric theory. So this is for the matter sector. So let's go back to the action. So if we look at this action, okay, so here I can't explain why there is no spin connection. But one important property of this action is that it is invariant under these infinitesimal transformations. So these are supersymmetry transformations which relate the transformation of x mu gives psi mu, and the transformation of psi mu gives a derivative of x mu. And here epsilon is a constant anti-commuting infinitesimal Majorana spinor. So this action has a global worldsheet supersymmetry. So the supersymmetry parameter epsilon is constant. Yes.
So the fact that the spin connection vanishes is an algebra consequence of Majorana.
No, it's not that the spin connection vanishes. It's that this term in the action does not contribute, but there is a spin connection. The spin connection does not vanish. What vanishes is the term in the action which would be proportional to the spin connection.
Is it necessary to have a bosonic degrees of freedom for this to happen, or could we construct a purely infinite theory, let's say, for another application?
No. Now I will discuss the gravity, because the spin connection refers to the gravity sector of the theory. So far, I discussed only x mu and psi mu, which would be the matter part, let's say. So now I come to the gravity part. So we would like to couple this supersymmetric matter action to two-dimensional supergravity.
Sorry, just trying to understand the equation that's written about. It's psi bar, rho alpha, omega alpha.
This one. This one?
Equals to minus itself.
Yeah, right. It's because I applied this.
But that's the spin connection term, omega alpha.
Right.
So how come it doesn't vanish if it's equal to minus itself?
Right, it vanishes. I'm trying to explain here why here there's no covariant derivative, but just ordinary derivative. Because the term containing the spin connection has to vanish because it's equal to it. Yes?
In one of the earlier lectures, they said that sometimes you can have fermions, but on shell you have at least in some cases half the degrees of freedom. So by looking at this action, in a moment you said, so I'm going to add d bosons, scalar fields, because I want them to be the same. Is there a way I can tell by looking at the action that on shell it's going to be reduced, or it's going to be exactly the same?
So on shell we can eliminate this auxiliary field. So this auxiliary field can be eliminated because the equations of motion just put it to 0. So on shell only these two are enough. But off shell we have to consider the auxiliary field, and we'll see the same thing happens with the supergravity sector. So okay, so let me go back to this action. So this action has this global supersymmetry. Because the epsilon, the supersymmetry parameter, is constant. So, of course, a basic fact about supersymmetry is that the commutator of two supersymmetry transformations gives a translation, And in this case, it is a translation on the worksheet. Okay? So, and here the parameter A alpha here is this product, epsilon 1 and epsilon 2 are the supersymmetry parameters of the first and second transformations. And so here it has this form. And then again, to show this is one of the exercises that I have given you. To show this relation, you have to use again this spin flip property. We will be using it many times. And similarly, the commutator of two supersymmetry transformations on the fermions gives again a translation on the fermion. And here we have to use the Dirac equation, the equation of motion for the fermions. Okay, so now there are no more questions. Let's go to the supergravity multiplet, which consists of a Zweibein. Here, Zweibein is like the square root of the metric. Say, for instance, we can. So the Zweibein. I don't know if you are familiar with this, probably. So the Zweibein is two in German. So I will call it line because it's too difficult to remember. So it has a curved index, alpha, and a flat index. Here AB is a flat index. So it's an index of the tangent space, and alpha, beta are curved indices, and the product of two bines give us the metric in 2 dimensions. Okay, so the supergravity multiplet contains the Zweibein and the gravitino, because I don't write spinor indices.
Excuse me. Eta sub alpha beta, it's another metric. It's a
Minkowski metric in 2 dimensions.
Minkowski metric. Okay.
Yeah, -1.
And the other metric, the H, is the induced metric?
It's a curved metric. It is the 2-dimensional metric, the metric on the worksheet.
Okay.
The curved metric on the worksheet. Okay, so the supergravity multiplet in 2 dimensions contains the Zweibein and the gravitino. So if one wants to formulate a theory with fermions in on a curved manifold, we need to introduce the bines, because basically because the group of general linear transformations does not have spinor representations. Okay, whereas the tangent space group is SON, so -1. It does. So we need this bine to convert curved indices to flat indices in order to discuss fermions on curved manifolds. So the bine in 2 dimensions has 4 components. So it is a matrix with 4 components. But the theory, if we look at this action, the theory has reparametrization. So as I mentioned, an important fact of string theory is that the 2-dimensional action has to be reparametrization invariant. So it cannot depend on the way we define the 2-dimensional coordinates, sigma and tau. We can transform this sigma and tau to arbitrary functions of sigma and tau, and the action has to be invariant. So reparametrization invariant provides 2 parameters. So we can use this symmetry to eliminate 2 of the components of the 4 components of the bine. And moreover, there is one local Lorentz transformation, which we can also use, and we can eliminate 3 of the 4 components of the bine. So this leaves only one bosonic degree of freedom. Okay, so let me I'll write it here. So we have the bind has four bosonic degrees of freedom, but we will use reparametrizations which we can use reparametrizations to eliminate two of the four components and Lorentz transformations on the worksheet, which has one parameter to eliminate another one. So if we use the symmetries of the action, we are left with one bosonic degree of freedom from the bind. Now the gravitino, which is the super partner of the bind, is a worksheet vector and a Majorana spinor. So it has, in n dimensions, it has 2 to the n over 2 times n degrees of freedom, fermionic degrees of freedom. So n is because it's a vector, and 2 to the n over 2 is the number of degrees of freedom of the Majorana spinor. So these are fermionic degrees of freedom. 2 to the n over 2 times n, in which, okay, so for n equals 2, this is 4, no? 4 fermionic degrees of freedom in 2 dimensions. And so for n equals 1 supersymmetry, there is again the parameter, the Majorana parameter of supersymmetry, which has 2 to the n over 2 parameters. So q to the n over 2, which in 2 dimensions are 2. So we have 2 degrees of freedom from the supersymmetry parameters. So we are left with 2 fermionic. So we can use this supersymmetry transformation to gauge away 2 components of the gravitino, and we are left with 2 fermionic degrees of freedom. So again, we have one bosonic degree of freedom, 2 fermionic degrees of freedom. We need an auxiliary field, an extra auxiliary field, which is usually called A, in order to match the number of bosonic and fermionic degrees of freedom. So the complete off-shell supergravity multiplet requires the introduction of this auxiliary scalar field. And again, the complete off-shell multiplet is given by the bind, the gravitino, and this auxiliary field. But again, on shell, we can eliminate this auxiliary field, and these 2 fields provide the complete supergravity multiplet in 2 dimensions. Okay, so this action, which I wrote here, we said it has global supersymmetry. So it is not locally supersymmetry. So local supersymmetry requires the introduction of this extra field, the gravitino. So it requires this. I'm not going to write this because it's too long and I'm going to eliminate it. So it requires an interaction of the gravitino, the Majorana spinor, and the X-min. So in order to have a local supersymmetry, we need to add to the action this term, basically the coupling to the gravitino. And this complete action has local worksheet supersymmetry. So here notice that I have not written a kinetic term for the gravitino, because again it vanishes identically in 2 dimensions, because the kinetic term for the gravitino would read like this. So I will write it here. So it would be gamma, alpha, beta, gamma, where this gamma is the product of 3 this would be the product of three Dirac matrices. Antisymmetrize. So this would be antisymmetrize. And of course, this vanishes in 2 dimensions, so this is why there is no kinetic term for the gravitino in 2 dimensions. So the complete action, which has local worldsheet supersymmetry, is this one, which is written here. I will leave it. Questions?
But your document once again, what does this?
Because in 2 dimensions we only have 2.
I know we have only how is this related to the fact that there is no physical?
Because how can we antisymmetrize? We have row 0, row 1, and we have left row.
No, I understand. But what is the origin of this term? The action?
This would be the kinetic term for la gravitino would have this form. It usually has this form. When you formulate supergravity in higher dimensions, this is the kinetic term for la gravity. But here in 2 dimensions,
Why does it happen that it has only one derivative, usually identical terms with the derivative?
no, for the fermions, it has only one. Okay, so this action is invariant under the following local worldsheet supersymmetries. Supersymmetry, now here the supersymmetry parameter epsilon is a function of the 2-dimensional coordinates, sigma and tau. Okay, so it is a Majorana spinor, but it depends on the worldsheet coordinates. And so local supersymmetry, again, it relates x mu to psi mu to the derivative of x mu plus one term containing the gravitino and psi mu. And of course, it relates the bind to the gravitino in this way. And the supersymmetry transformation of the gravitino equals the covariant derivative. This is a covariant derivative with torsion. I will discuss it briefly on the supersymmetry parameter. So this action, which is written here, this action is invariant under this local supersymmetry. And here this covariant derivative, okay, so this covariant derivative contains a spin connection, but the spin connection has a torsion piece, which depends on the gravitino. So the standard spin connection is obtained from the bind. This is basically a contraction of the bind with derivatives. So let me show you again the local supersymmetry reaction. This is again an exercise for you to show that the action is invariant under these transformations.
The bar on the parameter is also the
This is
row matrix.
Yeah, this is a Majorana spinor, so the conjugate is the adjoint times rho 0.
Supergravity basically is turn the global supersymmetry into a local supersymmetry. Every time we do it in our classical fields like electromagnetism or something like that, we just have to add a covariant term into the derivative. Can I see this action in that way in a subspace formalism, for example?
Yes, actually, this action is the action for a superspace in field, for a superfield in 2 dimensions. There's a superfield containing a bosonic degree of freedom and a Fermi degree of freedom. So one can formulate all this in superspace, digamos, a superfield, in a superfield formulation. Yeah, it is.
And the covariant term would be, what would be the covariant, the new covariant term to make
No,
it locally?
so the covariant derivative here would appear here, no? So this here is a covariant derivative. But as I said, in particular in 2 dimensions, it vanishes. But the connection here is the spin connection. So this is the spin connection. This is a connection for transformations for diffeomorphism, coordinate transformations, so which is the symmetry. And like in, say, in a gauge theory, you have gauge symmetries. Here it's a diffeomorphism invariant, which determines that the bind is giving you the
Great.
Okay, so another symmetry of this action is bind transformations. So under bind transformations, the 2-dimensional metric, so the metric scales with a factor depending on the 2-dimensional coordinates, scales in this way. For instance, if I take this scale factor to be the exponential to lambda, the fields transform like this. X mu has not transformed under bind transformations, but the spinors, psi mu and chi, transform in this way, because this is a spinor and this is a vector spinor. So one transforms like these are infinitesimal transformations. So this transforms like minus 1/2 lambda psi mu, and this plus. And of course, the bind, which is the square root of the metric, transforms in this way. So this action, so the full action is invariant under these bind transformations. And moreover, it's also invariant under these super bind transformations, where here eta is again a Majorana spinor parameter, and it depends on 2-dimensional coordinates. And all the fields are neutral, do not transform under this super bind transformation, but the Gravitino transforms in this way. So, moreover, the action is also invariant under these 2-dimensional Lorentz transformations. So again, under Lorentz transformations in 2 dimensions, the x mu do not transform, these do not have Lorentz indices, but the fermions transform as it should for a fermion. And the bind, again, it has a flat index, so it transforms like this. So the action is invariant under worldsheet Lorentz transformations. And of course, it is also invariant because we constructed it like that to be invariant under reparametrizations. So this psi is an infinitesimal parameter on the vector parameter on the worksheet. So under reparametrizations, the x mu and psi mu transform as scalars in this way, and the bind and the Gravitino transforms as vectors. They have a vector index. So again, the action, of course, we constructed it so that it is invariant under 2-dimensional reparametrizations. It cannot depend on the way in which we choose our coordinates on the worksheet. And so all these symmetry transformations, they can be derived in different ways. One way is the Nether method, which is probably you know from field theory. And you can also use superspace techniques, which are usually very powerful to do this. And okay, so an extra symmetry of the action is global space-time Poincare invariance. So so the x mu are transformed in this way under the Poincare transformations. Here, A mu nu is an anti-symmetric matrix for rotations, and B mu is for translations, a vector. The two-dimensional metric, of course, it has no space-time indices. It doesn't transform. This Majorana spinor are transformed in this way as a vector in space-time, and Gravitino has no space-time index.
Disculpe, según lo que mencionaba hace un rato, el gravitino es el partner de la tetrada que está usando, ¿cierto? Si la tetrada está relacionada con la métrica, entonces supongo con el gravitón, ¿no? Y este tendría que tener un spin 2.
No, no. Con el graviton no, o sea, con un supuesto graviton en dos dimensiones, pero no es el graviton espacio-tiempo. Esta es una simetría espacio-tiempo.
Claro. Sino que mi pregunta iba, entonces si usted mencionó que el gravitino era un fermion, supongo que debe tener asociado un spin o 5 medios o 3 medios.
3 medios.
En ese caso, si es 3 medios, ¿por qué no tome en cuenta de 5 medios? ¿Cuál sería? O sea, ¿por qué 3 medios y por qué no 5 medios?
Es que no hace falta para tener una supersimetría en dos dimensiones. Con estos campos podemos construirnos una acción supersimétrica con una supersimetría en dos dimensiones.
Eso cambia y se aumenta la supersimetría.
O sea, en este caso no hace falta tener campos con base finita.
Question.
En teoría, para obtener las reglas de simetría, ¿el teorema lineal se altera al pasar a trabajar con una supervalidad o simplemente es el usual teorema lineal que se aprende en campo?
Sí, es el teorema usual. Solo hay que tener en cuenta que los fermiones anticonmutan. Pero es el mismo procedimiento. ¿Más questions? Okay. So now we have this whole set of symmetries of the action, and so we can use these symmetries in order to gauge away some of the degrees of freedom of the bind and the gravitino. As I said, no? We will use these symmetries. And so I will show you how to do this. So, for instance, to gauge away two components of the gravitino, we rewrite the gravitino in this way. Okay, so here I add and subtract this term. 1/2 rho alpha, rho beta, chi beta. I add and subtract the same term, and I use the metric to change the index. Okay, so here I didn't do much. Now, from here to here, I use the Clifford algebra. So the Clifford algebra says that rho alpha, rho beta plus rho beta, rho alpha is 2 times h alpha beta. So this converts these two terms to this one. So I just switched rho alpha, rho beta to rho beta, rho alpha using the Clifford algebra. So this allows to decompose the gravitino into 2 terms. One term here, this term here is rho traceless, means that here, if I do this, so I will use this property here to say that this what I have called chi tilde, which is 1/2 rho beta, rho alpha, chi beta. This is rho traceless, means that if I take yes. So if I multiply this by rho alpha, then I use this condition here, it vanishes. So So here I can decompose, I have decomposed the gravitino into two pieces. One piece which is row traceless, and another piece which is here, lambda, I have called it lambda, which is basically rho alpha, rho beta, chi beta. And this corresponds to a decomposition of the spin 3/2 gravitino into components of helicity plus or minus 3/2 and plus or minus 1/2. So this is just a decomposition. So now the same decomposition can be made for the supersymmetry transformation. Recall the supersymmetry transformation of the gravitino was written in this way. So again, for this covariant derivative, I can use the same trick. I can define this operator here, which I have called phi. Again, adding and subtracting this term. This operator maps spin 1/2 fields to row traceless spin 3/2 fields. Okay? So so the supersymmetry transformation of the gravitino can also be decomposed into a spin 3/2 row traceless part plus spin 1/2 part. So I can write the helicity 3/2 part of the gravitino in this way in terms of spinors and spinor kappa, and then I can eliminate this part by using the supersymmetry transformation. Okay, so I can eliminate the helicity 3/2 part of the gravitino, and I am left with only the helicity 1/2 part. Okay, by using the supersymmetry transformation. Okay, so what I have done again for the bind, I can also use reparametrizations and local Lorentz transformations, as I said here, to get rid of 2 of the 4 bosonic degrees of freedom. So I can, so I am left with only 1 after using also local Lorentz transformation. I can write the bind as some term proportional to a delta function. So it only has 1 degree of freedom, which I have called phi. And so in this way, I get to what is called the superconformal gauge, which we will write here. The superconformal gauge, the bind can be written in this way, proportional to a delta function, and for the gravitino, we are left only with the helicity 1/2 part. Now, in the classical theory, I can still use Weyl invariance. So recall the theory also has a Weyl invariance and a super Weyl invariance. So I can use Weyl invariance in the classical theory. In the quantum theory, this symmetry will be broken. But classically, I can use Weyl invariance to get rid of this term in the bind. So let me say classically, Weyl invariance allows to gauge away all the components of the gravitino. I mean, from the bind, basically take a delta function, and super Weyl invariance allows me to get rid of the gravitino. Okay. So basically, after all this long trip, what we end up with in the superconformal gauge, the action takes this form, where now, since the bind is a delta function, so this means here I can take delta function. And I have eliminated the gravitino. So this action here is the action for the fermionic string with, in which the gauge has been completely fixed. Okay, so I used the symmetries of the theory to gauge away the gravitino and to put the metric into basically a flat form, the two-dimensional metric. Okay, so this is the action we will work with, but we cannot forget that we have chosen a gauge. So we cannot forget that this action is gauge fixed. So we basically eliminated the metric, the two-dimensional metric and gravitino, but we chose a gauge, and similarly as in the bosonic string, we cannot forget that those fields are there. So actually the equations of motion for these fields, for the metric and the gravitino, will be constraints on the theory. Okay? Okay, so now the worksheet indices will be raised and lowered with the flat metric, and basically the Dirac matrices will be just the constant row matrices.
So this action, where you use the superconformal invariance of the gravitino, this is still locally supersymmetric.
Well, it is gauge fixed, okay? So the full action contains the gravitino and all the components of the line, but I have chosen a gauge, and so the theory is gauge fixed. It is restricted, so I cannot, I have used the symmetries. We will see that I have not completely used them. There is some residual symmetry, which will allow me to make some additional gauge choice. But I have used most of the symmetries to gauge them.
Can you repeat the statement later with the constraints after gauge fixing? Because you suppose that we need to do that at the level of the equation of motion, not at the level of the action.
Sorry?
So can you repeat the statement related with the constraints after gauge fixing? If we do the gauge fixing at the level of the equation of motion,
No.
the resulting equation of motion are the same as the
No. I will first construct the equations of motion for the metric and the gravitino, and I will set them to 0, and I will use them as constraints. Okay, I will use them as constraints on the states of the theory or on the solution of the other equations.
What this means that the equation coming from this action are not the same than the original after the gauge fixing.
Right. Here I have lost the equations for the metric. Yeah.
So this is not in fact a real effective action for the real equation of motion.
This is a gauge.
Additional constraint.
Right. This is a gauge fixed action. I will now use write the constraints. Right. Okay. So let us write the constraints. Let us write the equations of motion. Okay, so the equations of motion for the x mu are similarly as in the bosonic string, are the wave equation, and the equations of motion for the fermion is just the Dirac equation. And of course, this equation, these are the equations of motion. And of course, these have to be supplemented by the boundary conditions. So I will discuss the boundary conditions later. Again, as I said, we cannot forget about the equations of motion for the metric, which will give me the energy momentum tensor, and for the gravitino, which will give me what is called the supercurrent. Okay, so these are actually the equations of motion of the action without having fixed the gauge, I can obtain the equation of motion for the vine and for the gravitino. But since I have gauged them away, this now they turn out to be constraints on the solutions of the theory. Okay, so in a theory, when the theory has fermions, the definition of the energy momentum tensor is basically the variation of the action with respect to the vine. So this way, this E is the determinant of the vine.
To go to symmetry, why we need the boson clear? Why we need to ask that the metric in the worksheet is an external of the action? Why we need to
Also, the equations of motion are usually work like that. No?
Yeah, but at the bosonic level, the variables are the invariants. Why we need to ask that also the metric is an external of the action?
So this, you can think of this, say even in the bosonic string, you can think of the Polyakov action as an action for two-dimensional field theory of scalar fields, say scalar fields coupled to gravity in 2 dimensions. So the equations of motion for this theory are the equations of motion for the scalar field and for the metric. So
in some way, you can think of the metric in the worksheet as the induced metric from the background. So it's something which is
no, not from the background. No, so the background metric is this one here, no? So this is the metric. So
the
H.
induced one on the worksheet.
Yeah, induced on the worksheet.
On the worksheet
So it's
from the background.
yeah.
So it's fixed.
No, it is not fixed.
You have
It is
you can build
it is a degree of freedom, no? So this is just a function of sigma and tau.
Yeah, but you can build if you have the invariants. It's the thing of this metric, like the induced metric in the worksheet, you can build. If you have the invariant, you can build this metric. So it is in some sense this given. No.
I would like to do a comment with respect to that. One can think this H as another dynamical variable if you interpret this Polyakov action as a two-dimensional field theory.
Right.
So if I understand your point, this H is another
It's another field.
Another field.
Yeah,
I would say.
right. Yeah, we have.
So you have basically the H field, the embedding, which describes the X, which are the other fields, and also the fermionic field. So from that point of view, and maybe you have some restrictions when you impose this stress tensor to 0 about this H, and maybe you can recover.
So this to 0 is the equations of the equation
This
of
is
motion
the equation of
for
motion for the H.
Right.
Yeah.
Okay, so maybe we can discuss later, but so this is the equations of motion for the brain and for the supercurrent. The supercurrent is basically the response of the variation of the action to the gravity, no? So I can write explicitly. One can write. I will not write it because it takes too long. But in the superconformal gauge, so here I'm using a flat two-dimensional metric. the superconformal gauge, the energy momentum tensor reads like this. This is the same as in the bosonic string, and then we have to couple to add the contribution from the fermionic sector in this way. And the supercurrent is basically the product of psi nu times the derivative of x nu. So it is also a fermionic field. Okay, now again, Weyl invariance implies that the trace of the energy momentum tensor equals 0, and super Weyl invariance implies that the supercurrent is rho traceless. Okay, so these two conditions follow from Weyl invariance and the super Weyl invariance.
¿Por qué digamos, el tensor el primero tiene dos índices y si entero supongo saldrá un vector para la conservación, pero en el segundo solo parece un índice? El F no es un índice, digamos, por ejemplo, para...
No, el F significa que es fermiónico, es la supercorriente, la indico como T sub F.
Y la conservación,
tiene
la conservación es integrar, da un escalar, digamos, o por ejemplo, al integrar para obtener las cantidades conservadas, me va a dar el primero un vector, una cantidad vectorial y el segundo sería un escalar.
La conservación va a dar la derivada de covalente. No sé si está claro. La conservación son estas expresiones.
Sí, sí, solo que lo mismo la carga, digamos, al integrar sobre el espacio. Digamos.
Ah, bueno, ahora voy a hablar de las cargas. Sí, ahora voy a... Sí, por ahora estas son las corrientes de simetría, de las transformaciones, de las reparametrizaciones y de las transformaciones de supersimetría. Son las corrientes. Ahora voy a hablar de las cargas. Okay, so here the conservation, so these currents are conserved. And again, if I write the conservation equations in the conformal gauge, the covariant derivatives, they just amount to ordinary derivatives. And so this, we will see that these conservation equations lead to an infinite number of conserved currents, conserved charges, an infinite number. And to show that, let me use light cone coordinates in 2 dimensions. So I will define these coordinates, sigma plus minus. I think probably Barton did that. So I will define these sigma plus and minus coordinates as tau plus minus sigma. These are light cone coordinates on the worksheet. So the 2-dimensional planimetric in these coordinates is, we will take this signature minus plus. And in terms of these coordinates, it is minus, it is sigma plus, it is sigma minus. So the components of the metric are eta plus minus or eta minus plus are minus a half, and again eta plus minus, upper minus plus, sorry, plus 2. And the other components vanish, so eta plus plus, eta plus minus minus, and the upper components similarly, they vanish. And we can define the derivatives with respect to sigma plus minus. Will be, we can write them in terms of the tau and the sigma. So it is convenient to use these light cone coordinates on the worksheet. And then if I write the worksheet action, in these coordinates, I think Nathan wrote it. So in these coordinates, plus and minus, and then so here, record. So here, the plus and minus indices on the fermion are spinor indices, and here the plus and the minus are just these derivatives with respect to sigma plus minus. So, okay. So I can write the equations of motion. Equations of motion in these coordinates, they become just the plus, the minus x mu equals 0 for the x mu, and for the fermions, the minus psi plus equals 0, and the plus psi minus equals 0. Okay, so this basically this equation of motion. This is for the x mu. Everything is like in bosonic string. So this means that x mu can be split into right movers and left movers. Before I do that, let me write the components for the energy momentum tensor and the supercurrent. And similarly, minus minus. And t plus minus and t minus plus equals 0, because in these coordinates, these are the trace of the energy momentum tensor, which vanishes. And so, so you see that only the plus plus and minus minus components of the energy momentum tensor are different from 0. So from the conservation equations, which in the conformal gauge read like this, then we have that d minus d plus plus equals 0, and d plus d minus minus equals 0. Okay?
Tengo una pregunta. Las corrientes nos dice que son conservadas. Eso entonces nos dice que existen unas simetrías globales de la acción. En este caso, ¿cuáles son esas simetrías?
Son las relativizaciones, ¿no? O sea, las corrientes.
Para las dos, para el tensor de energía momento y para la corriente fermión.
Sí, para las dos son las relativizaciones. La conservación sigue de la invariancia de relativización. Okay, so for the supercurrent, and again we have T plus and T minus, and again derivative minus of plus and derivative plus of t minus equals 0. So all this.
Bueno, no sé si estoy bien, pero la acción ahí, en los términos con y el sí no lleva a la barra, ¿no? Sí.
Sí, lleva la barra. Sí.
Sí.
¿Por qué?
Porque en la transparencia anterior no la tiene. Ajá.
Ah, pero bueno, okay. Sí, perdón. Sí, no lleva la barra.
Sí.
Ya está usado.
Ese y el otro.
Gracias. Okay, then here from the equations of motion, we see that the x mu, basically, we can, the solution is a sum of right moving and left moving terms. So this implies that mu has a right moving part, which depends on sigma minus, and a left moving part depending on sigma plus. And for the fermions, psi plus derivative minus of psi plus equals 0 implies psi plus, this here has psi plus is a function of sigma plus and psi minus is a function of sigma minus. So the fields can be split into right movers and left movers. And here, the conservation equations here, they show that actually, again, t plus plus is a function of sigma plus only. And t minus minus is a function of sigma minus. And similarly for the supercurrent. Okay, and so the conservation equations imply that actually there is an infinite number of conserved charges because so if I multiply t plus plus by any function of sigma plus, it will also be a conserved quantity, and similarly here for t minus minus, and and the same for the fermionic currents. So so this implies that there are an infinite number of conserved charges, which will derive in a little while after I discuss the boundary conditions. There are no questions?
Questions? One is, one of the first transparencies, you mentioned that the conserved charges can be obtained either by the difference theorem, and you mentioned also superstate.
Yeah.
Perhaps, maybe not now, at the end, there was
Okay, yeah. Yeah, so the superfield technique is actually very powerful, but somehow it hides a little bit the field content of the theory, so that's why I prefer to do this more explicitly. But actually, the superspace techniques are okay, so let me derive the boundary conditions. So we obtain the field equations, but we still have to work out the boundary conditions. Say when we vary the action, when we vary we vary the action subject to this condition that the variations of the fields in the extrema for tau, let's say tau 0 or tau 1, or if we can do it from minus infinity to infinity in the time variable. So we will make the variation so that delta x mu vanishes in the extrema of tau naught and tau 1. So when we do this, the variation, we get one term which is the equations of motion, so it vanishes from the equations of motion, but we get a boundary term. So this term here has to vanish in order to guarantee that equations of motion are satisfied. And so the boundary term, this is the same as happens in the bosonic string. So the boundary term, there are several ways to make this term cancel. One way that it cancels is if the derivative with respect to sigma. So here I'm taking the coordinate sigma on the worksheet to take values between 0 and L, assuming the string has length L. So one way in which this boundary term vanishes is if the derivative of x mu with respect to sigma vanishes at both endpoints of the string. So these are Neumann boundary conditions on x mu, and this means that the endpoints of the strings move freely in space-time. We could also choose Dirichlet boundary conditions. I will not discuss that. Dirichlet boundary conditions, they are very interesting. They give rise to de Bruyn's, but they break Poincare invariance, so I will not discuss this. Probably Clifford Johnson will discuss that on Saturday. So, okay, so this is one way to satisfy the boundary conditions. And another way is if the fields are periodic. So if I take x mu at 0 and L take to be the same, and again the derivatives of the x mu. So the fields are periodic, and this, in the bosonic case, this gives rise to closed strings, and these boundary conditions give rise to open strings. Okay. So here we have to now do the same trick for the fermions. So we will do the variation of the action with respect to the fermions, again fixing the extrema in tau. And so we are left with this boundary term. So this expression here, psi plus dot delta psi plus minus psi minus dot delta psi minus, has to vanish at the endpoints at sigma 0 and L. It has to vanish. So there are several ways to make this happen. So for the closed string, periodicity implies that this term, all this term evaluated at sigma has to be equal to the same term evaluated at sigma plus L. And this condition is solved in this way. We can take psi plus equal mass plus or minus psi plus at sigma equals plus or minus psi plus at sigma plus L, and psi minus the same thing. We can take anti-periodic boundary conditions because these are fermions, so they anti-commute. We can take anti-periodic boundary conditions. So, and the same conditions have to be taken on all coordinates, on all indices mu, in order not to break Poincare invariance. We need all the fields to have the same boundary conditions. So if we take periodic boundary conditions are called Ramon boundary conditions. I will write this here because it's important. So psi plus are called Ramon boundary conditions, whereas antiperiodic boundary conditions these are called Schwartz boundary conditions. And again, as I said, Poincare invariance in space-time implies that if we take periodic boundary conditions in one direction, we have to take them in all directions in space-time, and similarly for Schwartz boundary conditions. Okay, so this I can write these two boundary conditions in this way. So basically, psi mu at sigma plus L, I can write it as the exponential 2 pi I phi, where phi equals 0 in the Ramon sector, and 1/2 for the Ramon sector, for the Schwartz sector. So if psi is real, no more phases are allowed, only periodicity or antiperiodicity. And since these conditions for the two spinor components are independent, we can take periodic boundary conditions for psi plus and antiperiodic for psi minus or whatever. So this, in the closed string, this gives rise to four possibilities, which are Ramon-Ramon, so periodic boundary conditions for the left movers and for the right movers, Neve-Schwarz, which is antiperiodic, or Neve-Schwarz-Ramon, Ramon-Neve-Schwarz. So tomorrow, when we construct the spectrum, we will see that these two conditions, Ramon-Ramon and Neve-Schwarz, will give rise to space-time bosons in the spectrum of the theory, whereas Neve-Schwarz-Ramon and Ramon-Neve-Schwarz will give rise to fermions. Okay, so now for the open string, if I have time, for the open string, again, this term has to vanish, but then we need to impose that the term vanishes on each boundary independently. So meaning at sigma equals at each endpoint of the open string, this term has to vanish. So this leads to these two possible conditions: psi plus equals to plus minus psi minus on one endpoint, and the same thing on the other endpoint. Okay. So and again, in order to preserve space-time Poincare invariance, we have to impose the same conditions on all the coordinates, on all directions. And so, again, without loss of generality, so the important thing is the relative phase between one endpoint and the other one. So we can take both endpoints with the same boundary conditions, or one with one and the other one with the opposite. So this actually gives rise to two possibilities. I can choose that they are periodic, they are equal at 0, and here in the other endpoint, this eta here takes values plus or minus 1. So here, if we take eta equals plus 1, this gives rise to the Ramon sector, where psi plus equals psi minus on both endpoints. And if eta equals minus 1, so we have plus and minus boundary conditions, this gives rise to the Neve-Schwarz sector. And we will see in the space-time, when we construct the spectrum, that the Ramon sector of the open string will give rise to space-time fermions, whereas the Neve-Schwarz sector will give rise to space-time bosons when we rewrite the spectrum. Okay, so I'll finish here. I chose it, I can choose anyone. I chose it to be the face, so I use that to fix the line. So the degree of freedom, I put it in a factor, in a scale, which can be eliminated by sorry.
Last question is, you mentioned super violent.
Yes. Right.
Is there such thing as a super violent tensor?
Super violent tensor. Super violent tensor. I don't know what you mean by super violent tensor. We have the super current, actually, the super current, which is the current related to, so this, well, I don't understand the question. I understand. Okay. But in 2 dimensions, you know, the metric has no propagating degrees of freedom, no? They have no dynamical degrees of freedom. So you only have the, say, the Ricci scalar. I mean, the Ricci tensor and the curvature tensor, they are all related. No. In 2 dimensions, yeah. Yeah, there is. So, yeah, for gravity in more dimensions, you have a violent tensor, but in 2 dimensions, you only have the...
Any other question?
Why do we always demand that to have the same number of fermionic degrees of freedoms that bosonic degrees of freedom? I don't understand.
So this is supersymmetry. No? So supersymmetry requires the same number of degrees of freedom, bosonic and fermionic degrees of freedom. So this is supersymmetry. It relates. So let's say in a supersymmetric theory, you have at the same mass level, you have the same number of bosons and fermions.
But why? Why is this way? I don't know.
Why?
What is any reason there is any
well, so you mean why do we do supersymmetry?
No. Why supersymmetry implies that there must be the same number of.
Okay. I think.
That was in my
Write down the anti-commutator 2Q, and you take the trace over to all the states, and that gives 0. So your trace of states with a -1 to the f, so that implies that there are as many fermions at every mass level as there is bosons. So it just comes from supersymmetry.